Hi, this is Mr. Sapone, and today we're going to learn how to calculate average atomic mass based on percent abundance. And the atomic mass of an element is simply a weighted average of all the different isotopes of a naturally occurring sample of that element. And for those of you who are students, you might be familiar with weighted averages. Grades are often computed using a weighted average. I do my grades like that. Your grades are certainly graded using a weighted average. Tests are much more significant than, say, homeworks or quizzes or lab grades. So suppose that homework counts for 10%, labs count for 20%, and tests count for 70%. If Pat has a homework grade of a 92, a lab grade of an 81, and a test grade of a 68, what is his grade? Now we have to weight these grades. We can't just add the three grades together and divide by 3. That would get an average somewhere around 80-ish. But the idea is his test grades are low, so those are going to throw off the other grades because the test scores are 70% of his overall score. And what you do is you simply take the grade and you multiply it by the percent that it counts, but as a fraction. So this was his quiz score, or actually this was homework, sorry. This should say homework. We have a homework grade of a 92, but homework only counts for 10%. So instead of 10%, I have 0.10 because I turned a percent into a fraction by dividing by 100 or moving the decimal twice. So 0.10 times 92 plus, and labs are 20%, so I took this decimal and I converted it back into a fraction by moving the decimal 2 places to the left. So we have 0.20 times 81. And of course the test was 70%, so I moved the decimal over twice, 0.70 times 68. And the average grade would be a 73. And that's how you do a weighted average. And we can do the same thing for elements. That's where we get this number down here, the average atomic mass. There is a simple formula. When we are calculating the average atomic mass, we need to take the fractional abundance of the isotope multiplied by its exact mass. Then you do that for all the different versions or all the different isotopes of the element, and you add them together. And that probably looks a little confusing now, but we'll do a few examples in a slide or two, and that should clear things up. So we have carbon here, and there's two stable isotopes of carbon, carbon-12 and carbon-13. Now, if we had 100 atoms of carbon, around 99 of them would be carbon-12, because carbon-12 makes up 99% of all the carbon we find on Earth, and carbon-13 makes up only 1%. So how would we calculate the average atomic mass? Well, since 99% of all the carbon is carbon-12, the average atomic mass is going to be really, really close to 12, not close to 13. It's going to be much closer to carbon-12. And all the elements generally have different isotopes, most of them anyways, have different stable isotopes and lots of radioactive ones that aren't stable. But hydrogen has 3, helium has 2, carbon has 2, nitrogen 2, oxygen 3, sulfur 4. And look at chlorine. Chlorine is probably one of the ones on this list where the isotopes represent a significant portion of it. All of these, 99% is hydrogen 1, 99 is 0.999 is helium 4, 99% is carbon 12, and so on. But for chlorine, about 76% is chlorine 35, and around 24% is chlorine 37. So there is a big difference there, so that will affect the numbers. But the idea is we have different isotopes, different versions of the same element based on neutron numbers. So how do we calculate the average atomic mass of carbon, which we do already know from the periodic table? Carbon has two stable isotopes, carbon-12, carbon-13, and we're going to use the data below to calculate it. So carbon-12 has an exact weight and atomic mass units of 12.000 and so on. Carbon-13 has an exact weight of 13.003355 AMUs. And we're given the percent abundances. So what do we have to do here to calculate this? Well, you take the fractional abundance of isotope 1. This is the percent abundance. To turn this into a fraction, you have to either divide it by 100 or realize that dividing any number by 100 just simply moves the decimal over 2 places to the left. So this is going to be 0.9890 times the mass of isotope 1, which in this case is 12, followed by whole bunch of zeros, which I won't write in, plus, then this isn't a fraction, we got to do this first. Now we're going to add it to the fractional abundance of isotope 2, which again, we can divide by 100, or you can simply take this decimal 2 places right there, and we'd have to put in a 0. So this is 0.0110 times the mass of isotope 2, which is 13.003355. And yes, this is all you really have to do. Multiply both of these sets of numbers together, then add them together. That's really all you have to do. It's not super complicated. And a cleaner version of this is shown right here. When you do the math, you should get 12.011 AMUs. And a perfect way to check this is to check on the periodic table. If you have a number remarkably different than the number that's on the bottom of the periodic table, you did something wrong, or your teacher gave you bad data. So again, just to make sure this is clear, we have nitrogen 14, nitrogen 15. 99.63% of all nitrogen is nitrogen 14. A very small percentage is nitrogen 15. How do we get the average atomic mass? Well, fractional abundance of isotope 1. Divide by 100, or just move the decimal over twice. So that's 0.9963. This one's going to be 1, 2, so 0.0037. So these are our fractional abundances. We converted percent abundance into fractional abundance. So isotope 1, 0.9963 times 14.003074. And again, you do this for the other side. You're going to take 0.0037 and multiply it by this right here. I have a cleaner version of this, so we'll show that now. So fractional abundance of isotope 1 right here times the mass of isotope 1 right here, plus fractional abundance of isotope 2 right here, times the exact weight or the atomic mass of isotope 2 right there. And you just add them together, you get 14.007. So not super difficult, just turning a percent into a fraction and multiplying and adding together the products. So we'll do another one. Element X has 2 natural isotopes. The isotope with a mass of 10.012 AMU has a relative abundance of 19.91. The isotope with a mass of 11.009 AMU has an abundance of 80.09. So we know in the first case we have a mass of 10.012 AMU, and the abundance is 19.91%. To get this into a fraction, decimal goes over 2 places. So this times 0.1991. And that's our first isotope plus the second. And the other slide we did these opposite, but it's multiplication, so it doesn't matter the order that you put them in. The isotope with a mass of 11.009 AMU times, as a relative abundance of 80.09, this goes over twice, so 0.8009, and you multiply these together, add them together, get your answer. And that comes out to be 10.81 AMUs. And that's all there is to it. That's how we do this. Magnesium, we have 3 isotopes in this case, and you do the same process. And I don't think we're going to do this one all the way out, but we're just going to show you how to do it. You take isotope 1, this is going to be over, that's going to be 0.78. This is going to move over again, this is going to be 0.10. This is going to move over. It doesn't matter that we have 3. Instead of doing it 2 times, we just have to do it 3. So it's this number right here times this number, all right? And of course, it's going to be this number times this number as a fractional abundance. These are percent abundances right there. We turn into a fractional abundance. And this number times this number And then you simply just add all of them together. This is isotope 1, isotope 2, isotope 3. So if there were 7 different isotopes, you would have to do it 7 different times. And if you get a result, you should just look for a result that is very close to whatever magnesium is on the periodic table. So that should more or less help you. The atomic mass of magnesium is 24.305. And when you look at the periodic table box, Mg 24.305, I said, you should get a number like this down on the bottom. So you should get something close to that. And magnesium should have 12 protons, if I remember correctly. Hopefully I do. So that is magnesium. That's how we do percent abundance. Hopefully that helps, Mr. Sapone.